Welcome everyone to the Fasteners and the Furious. My name's Lori Cook. I'm Manager of Educational Outreach with AWC. Michelle Camberone is going to be joining us in a little bit. Our accreditation information is here. And here's our course description. So a couple of years ago, we got the idea to do a webinar that was kind of a connections FAQ topic. That was our cornucopia of classic connection conundrums. We had a lot of success with that webinar. It was very popular. We had a lot of positive feedback. So we decided, let's do it again. So that's how this program came about. This is, and as you can tell, we like to have a little fun with the names on these. So this is the Fasteners and the Furious. We have our learning objectives for today. So I won't spend too much time. I'm going to assume everybody saw those when they signed up. As Marcy mentioned, we have some polls, and our first one is the easiest one because there's no wrong answer.
That's exactly right. So, oh, it didn't launch for some reason. Okay, 1 minute. There we go. So what is your profession? Architect, engineer, code official, fire service, builder, manufacturer, or other? So go ahead and let us know what you are. Whatever your profession, we are happy that you are here and hope that you find something of value to take back to your office or your field, wherever it is that you work. And as usual, I wait until about 80% have voted, or 30 seconds, and I have both of those. So let's see what we've got. I've got 74% engineers, 17% code officials, 4% other, 4% architects, and 1% fire service. We are delighted that everyone is here.
Excellent. Broad array of individuals, and welcome again. All right, so here's our outline for today. We're going to talk about fasteners. Obviously, we're going to start with some NDS provisions and things that are a little bit beyond the NDS, some philosophy and general things. And then Michelle is going to take over and talk to you guys about nails, specifically with the 2018 NDS changes that have happened in this latest update, and then also some detailing considerations. So first, let's talk just fastener talk. Here is a list of all the different kinds of fasteners that are included in US design literature. And when you're designing with the NDS, you see that some of these fasteners are actually included in the standard themselves. And then other fasteners, you need to obtain an evaluation report for the proprietary product typically. So this is something that you're probably going to hear Michelle and I say 100 times in this presentation. If a product is proprietary in nature, and that means that it's not manufactured in accordance with some standard. So an ANSI ASME standard for screws and bolts, or an ASTM standard for nails. Those are the ones that we reference in the NDS. If your fastener is produced according to some other production standard, or it's a proprietary product, then you need an evaluation report to determine the design values or the appropriate values for that fastener. So when we talk about the NDS fastenings, the first thing that most people are most familiar with are our tabulated shear values. And here's an example of two of them, some lag screws and nails. And we also have them for wood screws and bolts. In these tabulated shear values, there are some assumptions, all right? It's always important to read the footnotes when we're working with these tables. And in these tables, we have the following assumptions in terms of penetration. So for lag screws, the tables assume that the penetration, the fastener penetration, is 8 fastener diameters. For wood screws and nails, the assumed penetration is 10 fastener diameters. Now, the more astute of you might say, Lori, the minimum fastener requirements in the NDS are lower than that. than those tabulated values. And you're right. So if you have a lag screw penetration between 4D, which is our minimum allowable penetration for lag screws, and the tabulated values, you would simply divide the actual penetration, which is represented by that lowercase p, by the 8D assumed value. And then you would, for wood screws and nails, it's very similar, except our minimum penetration allowed for wood screws and nails is 6 diameters as opposed to 4. But again, it's a similar adjustment that would be applied if your fastener has a smaller penetration than what is assumed in the tables. So again, these tables are for either a 8D or 10D for lags, 8D for lag screws, 10D for nails. And if your penetration is less than that, you'll need to apply that adjustment per the footnotes of the table. Dowel length is another another question that we get a lot when it talks about what length do I use for my fastener calculation. So there's actually two different, it depends on which way the fastener is loaded. There's two different ways of handling it, addressing it, that question. For fasteners in withdrawal, for lag screws, we talked about that minimum penetration is equal to 4 diameters. For lag screws, we do not include the length of the tapered tip in that 4 diameters of penetration. Wood screws and nails are a little bit different. We do include the length of the tapered tip. However, for any fastener that has a deformed shank or threads, basically, rings, something other than a smooth shank fastener, the actual length for withdrawal that you are going to be using is not the full fastener length, it is the length of the threads. So if you have a fastener that is only partially threaded, you would only use the length of the threads and either the length of the tip or not, depending on what type of fastener it is in withdrawal. In shear, the length would be, it wouldn't be based on the threads, it would be based on the actual fastener length. You are permitted to use 1/2 of that tapered tip length in the fastener length for these tapered tip fasteners. Now, for lag screws, the actual tip length is published in NDS Appendix L. For nails and wood screws, we assume the tip length is 2 diameters. So that's another one of those differences that you'll want to be aware of. So for lag screws, again, NDS Appendix L publishes the dimensions of all the lag screws, and the nails and wood screws, we just assume 2 diameters is the tip length. Now, when we're designing wood, it's important to understand some of the basic concepts of how wood behaves. And if you think of wood as a bundle of straws, that's a really good analogy for the way that it's behaved. Because if you look at a piece of wood under a microscope, you'll see that the cells in the wood are round or elongated, and they're tube-like. And it means it gives us very good strength parallel to the axis of the straws. Perpendicular to the axis of the straws, we don't have very good strength. It's easy to crush in that direction. In the case of wood, it's especially easy to get in between those straws and split them, right? That's where wood is the weakest, is that tension perpendicular to grain. So if we keep that in mind, if we keep in mind that our bundle of straws is very strong, parallel to the axis of the straws, but the straws themselves are prone to separation if you try to stick something between them, we use that philosophy when designing our connections and understanding what causes splitting in wood. So splitting happens because, again, the wood is very weak perpendicular to grain when compared to the other directions. So if we have nails closely spaced, like we see here in this illustration on the right, it's going to cause splitting when they're all in a straight line like you see here. They act as a wedge. Now, our next slide here, we talk about staggered nailing as a way to minimize splitting. Now, looking at these two illustrations, and there's not any sort of poll question, this is just for your own thought process, would you say that both of these show an example of staggered nailing? So something that surprises people, and oftentimes, it's not just people who are new to wood design. This is something that we've gotten people that have been designing wood for a number of years have tripped up on this. So the illustration on the left is an example where the nailing is not staggered. And this is something that we've shown in other presentations, so some of you might be familiar with this. The reason that this nailing is not staggered is it is offset in the kind of east-west direction on our page here. But if you look at the center line of the nails, these nails are all in one line. So they can act as a wedge between the grain of that member. If you look at the illustration here on the right, the nail heads are ever so slightly offset from that center line. And that is typically enough to help prevent that and minimize the effects of splitting. And this is actually something that is called out in our special design provisions for wind and seismic, or you might hear us refer to it as SPDWS. So in SPDWS, this is a graphic of how nails can be driven at a slight angle, and in this illustration, it's slightly exaggerated, so for graphical purposes, but this shows that you can achieve the proper edge distance of the nail and still ensuring that the nail is fully penetrating into the framing. So this is one way to help address that, and it is, again, it's in the commentary of our special design provisions for wind and seismic. All right, so here's three different illustrations, three boards that have different numbers of nails in them. And we already talked about splitting happens because wood is relatively weak perpendicular to grain. However, you're not going to split the wood in the perpendicular to grain direction. So the splitting itself is always going to occur parallel to the grain due to the perpendicular to grain weakness, which does seem a little backwards, but if you think about it, it does make sense. So we get these splits in between our grain lines basically, and the nails wedge in, and they cause splitting parallel to grain. So even though these two nails here are much closer together than the top and bottom rows, we're not going to see splitting in between these two nails in these tightly spaced rows. So in this middle board even, you'll see we have fewer nails, but we still have split them due to that linear arrangement of the nails. So our third board here, we see the staggered nails where the center line of the nails is slightly offset. And again, that minimizes the splitting because we're not having the nails behave as a wedge. All right, here's our next poll question.
Okay, so the staggered shear capacity for the fasteners is based on which of the following assumed penetrations? Is that 8D for lag screws, 10D for wood screws, 10D for nails, or all of the above? Excellent. It looks like people are paying attention. Fantastic. All right, I've got just about 30 seconds and 75%. So let's go ahead and close this and find out what we've got. So 88% have voted all of the above and just a little bit on the others. So I'm hoping that it's that all of the above.
It is all of the above. Congratulations to everyone that chose correctly. So again, this is for the, I should have clarified in the question. It was the tabulated shear capacity for the fasteners in the end. Yes, so we were missing a word there. But yes, for lag screws, we assume that the penetration is 8D, and then for nails and for wood screws, we assume for the tabulated values only, again, remember, that it's 10D. So, all right. Now let's go back to a little bit more of the wood connection philosophy. So we talked about how the wood is very strong perpendicular to grain, or very weak in that perpendicular to grain direction, rather. Wood is very good at resisting compression parallel to the grain, which makes sense because if you think about how a tree grows, the way it grows, it is resisting the most load parallel to the grain. So if we think of how the tree behaves and we exploit the benefits and the strongest mode of the wood, then we're able to capitalize on this idea, and we can produce economical designs that can still, as you can see in these photographs here, we can have very economical designs that can still be very architecturally pleasing. So when you're designing with wood, keeping in mind that compression parallel to grain is much easier to resist in wood than, for example, tension perpendicular to grain. So we keep that in mind when we're designing it, and we can build off of that. Another thing with mechanical fastenings is choosing the size of the fastener. So you need to keep in mind the scale of the fastener relative to the wood member size. So in general, it's better to use more smaller fasteners than it would be to, for example, use a large single fastener. So for something, where you're resisting it with a single fastener, sometimes we can see bearing or crushing failures underneath it, or depending above, underneath, whichever side of the fastener where it's bearing. So when we are able to reduce when we're able to reduce that load per fastener and spread it out, we reduce things like crushing at the fastening. We also are able to build in a degree of redundancy with multiple fastenings, which as engineers, we're all big fans of that, right? So this is an example of something, it's an okay connection, it's not a great connection. If you look at the fastener, or this connection here at the bottom specifically, for example. So the designer did a great job in avoiding eccentricity in the connection with this particular design. However, with just one large fastener, especially in a structure like this that's partially exposed, you can have things like thermal and moisture-related expansion and contraction that can induce stresses. So again, while this is not a terrible design, it can be made better by using more smaller fasteners while building in a degree of redundancy. There's a whole host of prefabricated connectors out there. Everybody's got their favorite manufacturer, so I won't get into one versus the other, but regardless of the manufacturer that you're choosing, their products will typically have this in common, that they use multiple smaller fasteners in their connections. So for this example, you see a column base and a column cap. Similar with joist hangers, these are all very useful products. They save a lot of time in the field, and they all, for the most part, will be using a series of smaller fasteners rather than just one or two larger ones. With metal plate connected trusses, these are kind of their own animal, if you will. The metal plates that connect these trusses are usually proprietary, And the people that are designing these trusses are usually working for the truss manufacturer. So most of us that are dealing with truss designs, or most of us that are dealing with trusses, we're usually not designing the trusses. And these metal plates that are used to connect the trusses, by and large, they cannot be modified in the field. For smaller things like where your truss bears on a hanger connection, for example, or other type of connection, you typically will have provisions that will allow nails to go through the truss plate. But in general, you are not allowed to modify those metal plates whatsoever. So for designers, that's usually less of a concern. It's more of a concern when you get out in the field and people get a little carried away with the Sawzall. Timber rivets are something that's in the NDS, and they have been used for decades, both in the US and Canada. They're not as popular in the United States for whatever reason, but they definitely have some benefits, and we do like to make folks aware of them. So the term timber rivet, despite its name, it's not actually a rivet made of timber like I thought it first was when I first started. So these are going to be large. There's spikes, as you can see in this figure here. There's large spikes that are used in conjunction with a steel side plate, and these spikes are hammered in through the side plate into your member. There are requirements that these would be used with glue laminated timber members, so you're not going to use timber rivets with solid sawn construction. It's used for larger members that have very high loads at the connections. Now, if you look into the research that was used in developing the equations for these timber rivets, it's, again, limited to glue laminated timber, but further than that, it's actually was done with Douglas fir, larch, and southern pine glue lams. So if you're using a species other than that, you may want to be careful, because the research has only been done on those two species of glue lam. The NDS does have some requirements for both the material and the geometry of timber rivets. So for the rivets themselves, you can see there are requirements in terms of the grade of steel, its ultimate stress, and they do need to be hot dipped galvanized. The side plates are minimum requirement of ASTM A36 steel, and if they're in a wet service environment, they are also required to be hot dipped galvanized. If you are in a situation where you're not in wet service, you may still want to consider using a galvanized plate or some other type of coated plate. And that's because when you have dissimilar metals in contact, they can cause preferential corrosion in one of the metals. So for this example, if we had a galvanized rivet and a plain steel side plate, because of the different types of metals, there could be some corrosion that occurs at that fastener. So you do want to take care to ensure that you're preventing that. And we'll talk about that a little more when we talk about treated wood as well. But there's a lot of applications, and here's just some applications you can see of timber rivets. And the capacities on these can be measured in the tens of kips, and that's a very high load, a very high capacity for a wood connection. And here's an example that Michelle actually found at a architectural firm office in Dallas, Texas, where we did see some timber rivets in use in the wild in the US. So they are out there, and if you guys are interested in using them, it's certainly something that can give you some more options in terms of your connections. All right, this slide is based off a question I got in the help desk not too long ago, and the asker was curious, why does TR12 provide dowel bearing strengths for fasteners of all sizes in plywood, but limits the fastener diameter to 1/4 inch in OSB? And that's referring to this dowel bearing strength table that is in Technical Report 12, and this bottom cell that you see in this excerpt here. I'll back it up actually. So Technical Report 12 provides an alternative set of yield equations for fasteners in shear. It gives you a few options that aren't available if you're using the NDS equations. The most notable being that the NDS requires that members that are using the yield equations be in direct contact with each other. The equations in TR12 can accommodate a gap between those two members. So if you have a gap or other material in between two wood members that has no bearing capacity, you could use these equations. But back to the larger question, why do we only have provisions for fasteners in OSB up to 1/4 inch? And that's because of the data that was gathered in the research of developing this. So OSB and also plywood, these sheathing, they're typically used with smaller diameter fasteners. So the large body of research on these materials is typically limited to smaller diameter fasteners. There has been some research done for larger diameter bolts up to 3/4 inch in plywood. And if you're interested in more information on that, you can take a look at APA Tech Note E825. So really the reason is that there's been more research done on large diameter fasteners in plywood than there has been in OSB. So we just don't have the information to go one way or another with it. Okay, the next slide here is the diaphragm unit shear capacities table, or one of them, from the special design provisions for wind and seismic. And Michelle's going to talk about this in a little more detail later. So I just want to brush on the fact that we do specify for diaphragms only common nails. So you see 6D, 8D, 10D common nails. So that's, if you are using this table from SPIDWIS, you have to use ASTM F1667 common nails, and the dimensions for that are included in NDS Appendix L. So you use the common nail size, and you also have to meet the minimum fastener penetration. You can't do just one or the other, you have to do both. So if it specs an 8D common nail with 1 3/8 inches of penetration, you would not be able to use something that is a different size that meets the penetration, that would be shorter than that 8D common. Similarly, for the shear wall tables, we again are limited to this time common or galvanized box nails. So again, these are the nails that are in accordance with ASTM F1667, but only common or galvanized box. So you're not going to see any sinker nails used in any of these tables, and we do not have tabulated values for roof sheathing ring shank nails in either diaphragms or shear walls. So if you're using these tables, again, you're going to need to use the common nail, or if you're in a shear wall, you're also permitted with the galvanized box nail. So if you're using a fastener that's not in the NDS, we've kind of bounced back and forth and talked about some of them that are and some that aren't. But if you are using a fastener that's not in the NDS, there are provisions in the IBC to allow that, and that's the alternative means and methods section of the IBC. So there are either manufacturer specifications or evaluated third-party reports that can be provided to the building official that they would have the discretion to approve or disapprove. So we talked about the yield mode equations somewhat. The yield mode equations are used for calculating shear capacity of any dowel-shaped fastener. So I mentioned there's a set in the NDS, there's a set in TR12. They are different, but they will give you identical results. So you could use either set as long as the fastener is a dowel-shaped fastener. You will need to know the fastener dimensions, and you will need to know the yield strength of the material. And that's something that's typically going to come from the product manufacturer. In terms of third-party reports, ICCES has a great searchable database. One ESR that I commonly direct people to is ESR 1539. That is the evaluation service report for power-driven staples and nails, and it's by ISANTA, and that's the International Staple and Nail Tool Association. They also have some additional resources on their website based around ESR 1539, so if you're looking for further information, there's some really user-friendly bulletins that they've got on their website here, and you can see the link on the slide. So here's an example of the nails that are covered in ESR 1539. So you'll see they discuss not only the shank style, they also provide smooth ring screw shank, various diameters as well as the sizes. And this is the report the table in the report that you would use for your diaphragm capacities. There is another one that's for shear walls as well. So this table in ESR 1539 would be analogous to table 42A from the special design provisions for wind and seismic that we took a look at earlier. So it gives you your fastener spacings, your seismic capacity, your wind capacity, and they provide it for both blocked and unblocked diaphragms. So it's pretty similar layout to what you'd be familiar with from SPIDWIZ, and it shouldn't be too foreign. Other ways you can search this, like I said, this ICCES website is really good. You can search by both the manufacturer or the product name. So here's a screenshot. I did a search just for wood screw, and I got several different ESRs with various different manufacturers. So again, that searchable database on their website's really helpful. Joist hangers are something I briefly touched on. These are, again, proprietary, so it's not just joist hangers, any sort of pre-engineered connector. They're proprietary, so they're not going to be covered by the NDS. And again, you'll need to get the capacity either from the manufacturer's literature or from a third-party testing report. And as with any proprietary product, the installation requirements are going to be per the manufacturer's specs. All right, fasteners in treated wood. And this is, when we say treated wood, there's typically two types of treatment we deal with. There's preservative treatment and there's fire retardant treatment. Preservative treatment we address pretty heavily actually in our Design for Code Acceptance, or DCA 6, which is our residential deck design guide. And the corrosion resistance requirements for that come out of the IRC. So they do specify if you're using wet conditions, if you're using preservative treated wood, the fasteners do need to have either a coating or they could be solid, whatever. So you can see the selection of different types of fasteners here. In terms of hangers and anchors, limited to be, again, galvanized and stainless, unless you get into that saltwater exposure. Again, it would be limited to stainless. again, this is another one of those places where you want to make sure if you don't have dissimilar metals in contact that are going to lead to preferential corrosion of one metal. So if you're specing galvanized hangers, it's probably best to just spec galvanized hardware as well. If you're specing stainless hangers, just go the extra mile, save the aggravation, spec all stainless fasteners. With fire retardant treatment, so the fire retardant treatment chemicals are again a proprietary product, and with proprietary products we need to talk to the manufacturer. So for fire retardant treated wood, we need to get the adjustment values, if necessary, from the pressure treater that applied the fire retardant treatment chemicals. There's some additional language in the IBC to govern fasteners and connectors in contact with preservative treated or fire retardant treated woods. I'm not going to go through the paragraphs that are in these sections. I just wanted to provide everybody with the appropriate code references so that if you did want to go in and see what was available, that would be available to you all. So these are the appropriate code references. So, all right. We got our third poll here, which Marcy's going to launch in just a second. But before she launches it, I just want to point out that for option A, we're talking about the design values from the preservative company. For option B, the design values are coming from the fire retardant treatment company.
Okay.
So, all right, go ahead, Marcy.
Perfect.
Oh, I think you might need to adjust your mic. You sound a little far away there.
Thank you. It was on top of my head. All right. So which of the following is true about fasteners and treated wood? So you need to obtain fire retardant treated lumber adjusted design values from the preservative company. Obtain fire retardant retreated lumber adjusted design values from the fire retardant treated company, or fasteners shall have corrosion resistant coating. All of the above, or answers B and C. You kept me busy on this one. These are a mouthful. Okay, so let's see. I've got 75 and 45 seconds, so let's go. Oh, sorry. And 60% answers A, B, and, or not A, B, and C, B and C. 27% all of the above and a little bit for the others. Which is it, Miss Lori?
All right, this one was tricky, yeah. So this one was definitely tricky. So it's B and C, and it was one of those questions. It was an SAT question. Sorry, guys, you had to pay attention to the wording. So if you are using fire retardant treated lumber, the adjustment values need to come from the fire retardant treatment company, not the company that is making or applying the preservatives. So that is one of those slight nuances. But congratulations for those of you that got it correctly. And now we're going to go ahead and turn it over to Michelle, and she can talk about some nails. And let me just, here we go. Okay, Michelle, we should be good to go for you.
Okay, yes, I believe you're seeing my screen.
Yep.
And as Lori mentioned, we'll be talking about nails. And we get a lot of questions about what's coming up in the 2018 NDS, and it has a lot to do with nails. Now, when we go to the job site, we see tons and tons of nails. We know there are different types of nails out there and from various manufacturers. But unfortunately, the NDS can't cover all of those nails, so we need to make some assumptions with developing the standard. And the standard is based on nails that are made per ASTM F1667, which is shown here. Now, we also assume a full round head, which is shown here. And that is because they are the typically referenced nail size in codes and standards of prescriptive tables. And so assuming that there is a round head. Now, some of these other heads that are shown here may see them on their website, on the job site, and because of the pneumatic nail guns, and some of them may even be covered in the ASTM standard. But as I mentioned, we need to narrow our focus on certain types of fasteners. And for those that don't meet the requirement of the round head, Lori had mentioned this previously, there's the ISANTA, which is International Staple and Nail Tool Association, that has an ESR report that can be very helpful with coming up with some capacities for shear walls or diaphragms. They have tables that look very similar that have capacities for these types of fasteners. The other thing that you'll see is that in the NDS, and in the 2018 NDS in particular, now we have a section that's covering smooth fasteners or smooth nails versus deformed nails. And what you see here, this is a smooth nail. In the previous 2015 NDS, it was noted as a plain nail. So we added a little bit of nomenclature, a little bit of change. So smooth nail, and then we have the deformed nail, which is new, the terminology of deformed. So, and this one shows a ring shank nail, which is also new to the NDS, and we'll get into why we're adding it, et cetera, et cetera. But these two, we have the smooth versus deformed. The other two nails are not covered in the NDS, but you may be able to find capacities for those in an ESR report. And key to that is when using those type of nails is submitting that documentation, obviously, to the code official, and the code official will have the final say on whether or not they accept those ESR reports. So now that we know that we have some assumptions for the nails, we need to make sure we specify in our drawings the proper information to define it as the type of fastener that you're using or assuming to use in your design. Because just calling something 10-penny common is not going to provide the exact information that's required, because there's so many different nails out there. In fact, 10-penny common nails, there could be 20 different 10-penny common nails. So to avoid any problems, we want to specify the penny weight, type, diameter, and we want the head and the shank diameter, as well as the length of the nails. And in the NDS, you can get that information from our table L4 that's in the appendix. And I believe Lori had mentioned that before. We also have in the wind and seismic provisions, table A1, which is, I believe, the same table, although the addition is off from the 2015 to 2018, but they're very similar tables. Now, one of the reasons why we have some pretty big changes related to nails has to do with the demand on our structures and the changes that have occurred in ASCE 716. And the NDS references ASCE 716. And it has to do with the wind loads. Now, we see a map here from ASCE 716 that probably looks a little bit different than the previous map in that it has more contours across the United States. And the reason the reason for this is now we have more info, or not we, but who are developing these criteria. There are more updated studies with wind data from over 1,000 weather recording stations across the country. So with that more information, we can have more accurate wind speeds across the nation. So more, I'll show you in the next slide, which shows just 110 here, 115 here. So you can see the wind speeds were just spread out under a common denominator, where now we have more accurate information. So in the Western United States, for example, California, you may see your wind speeds lower than what it was before. And there's a really good article by Donald Scott, and you can download it for free. It was published in Structure Magazine. He actually did a webinar for NCSEA that gets down into more detail related to the changes for wind load provisions. But one of the areas where we're seeing a change also is when it comes to components and cladding design loads. And what we see is that when we look at the components cladding coefficients, we see an increase in the shaded areas that are shown here. And to get into it more deeply, and it depends on the roof slope, etc. But you would see here, this is a table that was developed for this presentation, and it shows ASCE 716, a ratio of ASCE 716 versus ASCE 710, and the roof coefficients that include the external roof coefficient, which is shown here, as well as the internal. This column is just for the main part of the roof, and this is for the overhang. So anything over 1.0 is an increase in these roof coefficients. So you can see in the areas that I shaded, particularly the 1 zone, we have quite a bit of an increase, even as much as, well, 2 in some areas, and even up to almost 2.5, depending on the slope. So given that, we have higher roof coefficients, and using that, and this is assuming an enclosed structure. But will that really increase the demand on your structure if we have higher coefficients? Well, when we look at the equations for determining our maximum pressure, we see this Q sub Z, which is the velocity pressure at a certain height Z, and it has the wind speed right here. Then that is plugged into our equation here, where we convert it to conversion to ASD. And then we also include the composite and cladding coefficients. So if your wind speed stays the same and you're doing this components and cladding design, then your pressure will increase. But as I mentioned previously, some areas of the country, the wind speeds will decrease, and that would possibly offset that increase that we see in the components and cladding equation. So now we'll get into chapter 12, where we have some changes related to how are we going to provide proper detailing and a solution to these wind uplift loads on the roof, where there are certain areas of the country that we're going to see an increase in the demand on our structure. And that's where the roof sheeting ring shank nail comes into play, which is shown here. So we have now a new table, table L6, which shows the roof sheeting ring shank nail, has all the information related to roof sheeting ring shank nail. And note that the nomenclature for a roof sheeting ring shank nail is not a penny weight, it's called a dash number. And I'll show you in the next few slides. So when you call it out on your drawings, you'll know that. But I mentioned earlier about some clarification of the language, some introduction of language such as smooth nails versus deformed nails. So we've gone up and clarified the language in the section on nails. So in 12.1.6, we added the roof sheathing ring shank nails. We had specified ASTM. We need to meet the requirements of ASTM F1667, but we also now include supplementary requirements. So the engineered construction shall meet the supplementary requirements of ASTM F1667 related to S1 nail bending yield strength. And then also we are, so we have charging language for this. We have clarified that the nails and spikes need to meet the requirements of the supplementary. We are also requiring that the head diameters of the nails are needed to be included also in the specifications. Sorry about that. And then now we go to the section on the actual nails and the smooth shank nails or spikes. So we've made a delineation now that we have bright and galvanized carbon steel nails. So we included that. Also, we have a new section for stainless steel nails because the capacities between those two types of nails is very different. As you can see from this equation here, even though it's a little different, we've to the 5 seconds power where we have, or 5 halves power, where we have to the 3 halves power. But just that alone shows you that they are very different capacities. So we've clarified that, and this is all for withdrawal of the nails. And just to bring that idea home, we have on the horizontal axis specific gravity for the wood. So the southern pine would be 0.55, and then Douglas fir would be around here, 0.49 or 0.5. Hem fir is somewhere in between here. And then on the vertical axis, this is pounds per inch of penetration. Now the red is the carbon steel bright or galvanized nail, whereas the stainless steel is in blue. So you can see, depending on the actual specific gravity of the wood, we can have as much as a 40% difference in capacities of the nail. And this was all for, and this is withdrawal, but it's all for a smooth shank, 8-penny common nail. That this is a comparison. Same nail, different, same penny, 8-penny common nail as far as size, etc. But type of nail, different capacities, provides different capacities. So I believe we have a poll, and Marcy, do you want to go ahead and launch the poll?
I absolutely do. So stainless steel nail withdrawal equation produces higher values of withdrawal strength than NDS carbon steel nail equation. True or false?
Okay, do we have an answer?
We do. We've got about 30 seconds and 75%. So we have 86% that say false and 14% say true. What is the true answer?
Oh, great. And remember, you're not graded on these polling questions, but the answer is false. False. And just to go reiterate this answer, this is a comparison of carbon steel versus stainless steel, where you can see the carbon steel has higher capacity than the stainless steel. Okay, so we're going to continue on through. So we just went through the section on smooth shank nails, and now we're going through deformed shank nails. And again, this is all having to do with withdrawal. And we have now the roof sheathing ring shank nail that's included in our standards. And we have, we've included it in our standards. So we've updated our capacities to include the roof sheathing ring shank nail for withdrawals. And you can see there relative to the post frame ring shank nails. I don't think that's used as often. Now, the other thing is that the roof sheathing ring shank nail has been in the industry for quite some time. We're just providing it now in the NDS to help designers out now to provide ways of determining capacities for them other than going to an ER report. So now it's submissible for these different capacities that are provided. And also, we have now a additional failure mode for these type of nails. So previously we looked at the withdrawal of the nails, and it was the withdrawing of that nails from the main member. And now, however, these fastener head pull, because of fastener head pull-through data used to set industry recommendations for wood structural panels, and we combined with historical data from tests of lumber and plywood, it was used to analyze the development of these new fastener head pull-through provisions. So instead of looking at the nail as it withdraws from the main member, we're looking at the localized failure of it being the wood structural panel pulling up on that nail, and then there's a localized pull through at the head. And just to show you, well, let me cover this equation here first. So we have two equations. The equation is based on the diameter of the fastener, the diameter head, and then the specific gravity. And then we have the side member, the net side member thickness here. Now, depending on what your thickness of your side member is, that will tell you which equation to use. So a thicker side member would provide a higher capacity. And that makes sense because you're going to have more resistance with that thicker side member. So to give you an idea, now this is actually from a shear wall test, but it shows some nail head pull through in these localized areas. You see, here is where the nail was located. Here's another area where the nail was located, in another area. But the nail actually pulled through the wood structural panel. So analyzing these fasteners, now we have to look at the two equations, the two modes of failure, the withdrawal from this main member, and then the localized stress in this area and pulling through. And so as we have an example shown here, and this was done in MathCAD. I believe Lori did this, and we're going to look at both equations. So and determine the capacity of the nail. We will take the lesser of the two when we determine our capacities, because that's going to be the governing one. So we have a nail that's 0.131 diameter and then 3 inches long. The roof sheathing ring shank nail is 3 inches long. We have Douglas fir larch in the 2x6 member. The wood structural panel is 7/16 inch thick, and this happens to be an OSB rather than a plywood. And then the nail that we're using is a roof sheathing ring shank nail, and it's a dash number 5. It's not a pennyweight. The nomenclature is dash number. So then the key to this is when we look at our withdrawal, we're not using the whole length that's embedded into the main member. We're using the thread length, which Lori touched upon previously. So we go here, we go to this table, and this shows you the thread length here. And also, so here gives you all the information that's given that we get from the tables and from our side member, et cetera, et cetera. That's the given the equation. So first we're going to check withdrawal. We go to our equations and we see 1800 and the specific gravity squared and then d diameter. So this gives you the equation. You can also go to the table just to get to the equation, get the capacity. And here it is. we get the total length, or thread length, and then multiply times 59 gives us 88 pounds. So notice this colon equal. This is not anything. It's just something MathCAD does, just for your information. It's not a new term. Now let's look at fastener head pull through. So our side member is 0.438 thick, and then we do 2.5 times the diameter head, and that is, and then we take that will give us determine which equation to use. And so we see that plugging that into the equation, we have, well, here's the result of that equation. And we see that we have to use this equation 6a. Now that we have that, we plug everything into that equation and come up with a capacity of 67 pounds. So of the two, the governing one is the nail head pull through. So it would be interesting to see what would happen if we thickened up our wood structural panel. Perhaps that would probably increase our capacity of head pull through, but I'm not sure if it would make it greater than the withdrawal of the nail. Now, good news is we actually we do have tables with head pull through and withdrawal of the nails. And you can compare the two to find out which one's governing. This is a handy table that actually does the comparing for you. So it says minimum capacity of withdrawal or fastener head pull through is tabulated. Perhaps this might be incorporated in the NDS in the future, but right now it's in the wood frame construction manual, which can be downloaded from our website for free. It does not include the commentary, but it goes through and checks both equations and puts the governing capacity here, and does it for a common 8-penny common, 10-penny box, and the roof sheathing ring shank nail. Okay, so we have one more quiz, Marcy, or poll, not quiz.
Sorry, I lost my screen for a second. Let's go. All right, wood is strong perpendicular to grain and less strong parallel to grain. True or false?
This is a little tricky because it has to do with Lori's part of the equation. I mean, presentation.
All right, we're getting there. I've got about 10 more seconds. All right, I've got 75% and 30 seconds. So let's see, 80% false, 20% true.
So what is the answer? False. It was a little tricky, but wood is stronger parallel to grain and less strong perpendicular to grain. And a good way to, helpful way to remember this is those straws. Think of straws. If you apply a load perpendicular to those straws, it's going to be less strong than parallel to grain. And I like to think of it as a tree. When you think of a tree naturally in the outdoor environment or wherever, when a tree grows, it grows vertically and the grain of the wood is vertical. So that's going to be its natural, strong mode of resisting loads vertically. Okay, the next part of this has to do with detailing considerations. And we do talk about this in some of our presentations in the past, but every time we continue when we go out into the industry and give presentations and talk to people throughout the nation, talk to engineers. This is something that is often, well, I shouldn't say often, is sometimes missed. And even by very experienced engineers, even by very experienced wood engineers, they aren't aware of this section. So that's why we continue to talk about this. What it states is, and this is in section 11.1.2, stresses in members at connections. And what it states is local stresses in connections using multiple fasteners shall be checked in accordance with principles of mechanics. So if you have a group of fasteners, you need to use principles of mechanics. Now, how do you check those local stresses? Is there any method to check it? Well, one method to check it is in Appendix E. So it's not mandatory that you use Appendix E, but it's a really good, it spells out the different failures, modes of failures for engineers to determine, calculate this. So this is the Appendix E, and I'll go over what we're talking about. So here, it shows a very brittle failure and closely spaced fasteners. And through testing, it was learned that where a fastener group is composed of closely spaced fasteners loaded parallel to grain, so here, and this is a glue laminated timber member, loaded parallel to grain, the capacity of the fasteners may be limited by wood failure at the next section or tear out of the group. So there's 3 modes of failures. But when you think about it, if you're grabbing onto something and you just grab onto a small portion of something, that's not going to provide you as much capacity if you spread out your attachment to that connection over the surface of the member. It makes sense. You're going to grab more of that. Love the engineering technology there, but that kind of gives you an idea of what we're talking about. So here, when we have properly spaced fasteners, it increases the ductility of this connection and you get higher connections. So I know this just shows you, I mean, it did fail, but it has less connections and higher capacity. And so here we have the equations that are in Appendix E that look at, we have a net tension across the through this section of the wood member, and then row tear out here, all along the individual rows here and here. And then the third mode of failure, which is often, or not often, but can be the governing capacity for a connection of group fasteners, is this whole group here, depending on how closely spaced these bolts are. So let's look at a design example, and we have a 2x12 Southern Pine. Number 2 Southern Pine is the main side member, and then a net section check. So we're going to go through and do each of the checks that are provided in this Appendix E. So the holes we're assuming that it includes the 1/6 inch oversized maximum, nothing greater than that. And we can determine our area net based on that assumption. So we get a capacity here, or the 1.25, and then times 450 pounds per square inch. And then we also get a net section here, shown here. So understanding it, but this equation here, now Z net is the adjusted tension capacity of net section area, and then F sub T is the adjusted tension design value parallel to grain. So you would get this, you get the F sub T from the supplement of the NDS, and then the area obviously is what you assume when you look at your member or find out what that area net section is based on whatever assumptions to your drilling of that hole. Just finding out what left of that member is in your member. So that looked at that equation. And then we see here, looking at the row tear out, we have an equation that's provided. And we find out, again, assuming that a 1/16 inch over maximum driven over that, and come up with also the spacing between the rows of nails to determine what this happens to be 3 inches. Or I'm sorry, 4 inches here is what we came up with. As critical as the minimum of the edge distance and the in-row bolt spacing. So you could have an edge distance here or the row bolt spacing to come up with that tear out of the whole entire row. And then for the group tear out capacity, we have this equation. Z is the equation, Z group tear out, and then similar, we look at the whole net section around this area. So the area group net all around here to determine our capacity. And the resulting, looking at side by side, and I'm going to go, so this is I should have showed this in the first slide of what we're actually looking at, because this is splicing with a 2x member on top and a 2x member on the bottom, and then a load is applied here. So we want to transfer our load through this splice. But the next table really shows, really nails home the idea of what we're talking about when we're talking about group tear out. Now here we have the diameter of the bolts here. And then this is the net section tear out. So that's through the depth of the wood framing member. Then we have the row tear out shown here. Now that's the same for all the bolts. It's based on the spacing in that row. So that's the same. What we have here is the row spacing. That's the distance between let me go back to this. So when we go here, the row is this here, 4 inches apart, which is shown here. So when you look at this, you intuitively probably think, well, the 1-inch diameter bolt's going to give you more capacity. And when you look at this, yes, the multiple, that gives you the capacity of the actual bolts. But when you take into account the net section, the row tear out, and the group shear tear out, you can see smaller diameter bolts give you actually higher capacity. When we look at 4 inches on center, we have 6,418 pounds. But we decrease our spacing, our diameter of the bolts, and you can see we can gain as much as 200 pounds plus more capacity. Now, what if we spread that out across the surface of the member? Well, we increased it from 4 to 5. That means you're hanging on to more of that wood member, and you can see you get more capacity from the 1 inch with 4 inches apart versus 5 inches apart, you get a more capacity. But then smaller diameter fasteners as well give you higher capacity. So something to look at when you're looking at those a method for the engineer to design for localized stresses and checking localized stresses. Now we're going to move forward and look at other detailing issues that we have had come across the desk related to questions on detailing of force transfer around opening shear walls. So in the NDS, or the wind and seismic provisions, and the building IBC, we have 3 different types of shear walls. We have the segmented shear wall, which is just the full height shear wall. This could actually be a segmented shear wall designed as one and just not take into account any construction above and below the openings. We're just going to take in this full height pier. Now that's been around since going back to 1950. We have data on that. And then you have a hold down at each end. Well, the force transfer around opening takes into account the construction above and below the opening, but there are no prescribed methods for analyzing these type of shear walls. You're supposed to use a rational analysis for analyzing these shear walls. Because that we are taking advantage of that above and below the opening, we need to provide some additional detailing to make sure that wall acts as one whole wall rather than an individual pier. And then, of course, we have the perforated shear wall that looks at the entire wall. And there are limitations to this is in the code, spelled out in the code, and the wind and seismic provisions, actually. And it's based on a semi-empirical method that was developed based on shear wall testing. But there's anchorage, a lot of more anchorage involved at the bottom of the shear wall, just to make sure that the failure mode is up into the shear wall rather than at the base or the connection to the foundation. We want to make sure it's a ductile failure rather than a rigid failure at the sill plate. So given that, we have three different types of shear walls. The one that we're going to be talking about has to do with a force transfer around openings. Now, there's some advantages, and you see some efficiency in the design of a force transfer around openings. One of those being that you can have a higher aspect ratio, or the aspect ratio, not a higher one. The aspect ratio is based on the pier height at the opening rather than the full height of the wall. So for a segmented shear wall, the pier height is the full height of the wall. And for a perforated shear wall, I believe that I'm going to have to check that, but I think it's the full height as well. But for force transfer around openings, we can use just the pier height because we're treating this as an entire wall and we're providing additional detailing across the opening to make sure that our load gets transferred across the opening. So instead of it being 8 feet over 2, it's now only, say, 2 feet over 2. So we get a break there. And the other thing is this, as far as methods for analyzing force transfer around openings, there are other different methods out there. Again, there's no prescribed method for analyzing these shear walls. This just shows three different types of methods that may be or are available for analyzing it. And but when we look at the overall requirements for force transfer around openings, we have this note here, and that's where the issue that we're talking about comes into play. What it states is collectors for shear transfer shall be provided through the full length of the force transfer shear wall. So this is the limitations. So what does that mean? Collectors for shear transfer. And is it have to be along the whole length of the shear wall? Well, some have interpreted it as this. This is your force transfer wall. This is a force transfer around opening wall. And that this strap has to be along the full length of the wall. Well, the intent of that note is for the collector at the top of the wall that transfers shear forces between the diaphragm and the shear wall. It doesn't have to do with the strap around the openings. And so we remove that and we can have our straps right around the openings, not the full length. So typically you would have top plates that provide that collector element or strapping to have that continuous continuity of transferring that load from the diaphragm to the shear wall. So if you're interested to get further information about the force transfer around opening research, APA did some research back in, the study began in 2009 with APA, University of British Columbia, and then the USDA Forest Products Lab. And they did research. This publication came out in 2011. That's available on the APA website. All you do is you go to apawood.org. You have to have a username and password to create an account, but once you do that, you have access to all of their publications, or most of their publications. We also have a recorded webinar on our website that goes into more detail on the force transfer around opening design. We had APA partner with us on this webinar, and you can watch it. It's on our e-courses, and it's available for free to watch. You can earn continuing education credit if you pass the tests. And then there's a publication by APA that goes in, and I believe it provides an actual design example of the forced transfer round opening method that they determined based on the testing that was provided. And then there's a spreadsheet calculator that they provided for free that you can download. But I want to emphasize, this is one method that can be used. It's not prescribed in the code, but definitely a method that can be used, a rational analysis. So we're coming up on the end of the presentation, and we'll take questions after this. I'm sure Lori has gotten a lot of questions that have come in, and I've seen some questions come in. But for more information, we have the NDS that's available from on our website for free, excluding the commentary at awc.org. We also have a lot of helpful information. If you go on our website on the publications, there's a question mark. You click on that question mark and it leads to a article that was published in Structure magazine that goes over the significant changes. APA has a lot of information related to connections. Here's a publication for glue lamp connections. And then TR12, that's dear to Lori's heart, is also available. That's a free download from our website. We also have a connection calculator that's web-based that's available for free from our website. And then Lori mentioned the DCA6 that's available. That's probably our highest downloaded document on our website on decks, wood decks. And then, Lori, do you want to come back and we can talk about some questions?
Sure thing. All right.
We want to remind everybody to stay on to meet your time requirement to receive your continuing education credit too. Okay, right. So I had a question that came in earlier. Mm-hmm. Here's a question that, let me bring it up. Why building officials allow fasteners with code reports tested in only solid sawn lumber to be used with, say, SL, structural composite lumber?
SCL, right. That's a good question. And actually, if you look at the NDS connection provisions in Chapter 12, they do actually apply to structural composite lumber, to solid sawn lumber. Basically, they apply to every product that you can design the NDS with. So there aren't necessarily any adjustment factors that would be required separately from structural composite lumber compared to solid sawn lumber. So in terms of the behavior of a fastener in solid sawn lumber when compared to a structural composite lumber product, the structural composite lumber is at minimum going to exhibit equivalent behavior to the solid sawn member, but typically it's going to provide superior performance than a solid sawn member of equivalent or roughly equivalent size. Mm-hmm. So there would not be any concern for using something that's been tested with solid sawn with a structural composite product from that standpoint.
Yes. And I saw another question came in. Is there a Spanish version of the DCA6? And yes, there is. It's shown right here. We have Spanish version of the 2015 and the 2012. Awesome. Another question came in related to the use of adhesives for shear walls. Do you want to expand on that?
Yes, yeah, I can talk about that. So SPDWS has a specific prohibition on using adhesives with shear walls. Adhesives, glues, they tend to induce a brittle failure, which is, we know that that's the opposite of what we want. We want a nice ductile failure. In wood design, ductility comes from the connections, so we don't allow glue in shear walls for that purpose. You do sometimes see them used in diaphragms, and oftentimes what happens is, they'll lay a bead of glue down and then put this on the top of the joists and then attach the sheathing with nails. And from a structural standpoint, the glue is not adding any structural capacity. In my experience, what happens is in your linear elastic range, the glue can prevent things like floor squeaks, but it is not going to, like in an extraordinary load event, the glue will fail in a brittle fashion and then it'll just transfer the load to the fasteners. So from a structural standpoint, you're really not going to benefit a lot from using glue.
Yeah, and can you see my screen? So
Yes.
this is the section where it talks about adhesives, just for those that are interested. And it proves they could use it in low, where ductility isn't a critical challenge for shear walls.
Right, in low seismic areas. Yeah, I did forget about the exception. Good pull, Michelle.
That's what we do. We help each other out. Okay. Do you have any?
Let's see. All right. Questions. Can you give an example of what we would use fire retardant treated lumber for? Oh, that's actually a good one. You want to take that? Yeah.
Sure. So there's a couple off the top of my head that I can think that the code allows the use of wood in exterior walls, provided that the exterior wall is framed with fire retardant treated wood. And that has to do with type 3 construction and heavy timber construction. So type 3 construction is becoming more and more prevalent throughout our nation, because that's the type of construction where you see these 5, 6, sometimes 6 stories of mid-rise construction. And type 3 construction gives you larger buildings than, say, a type 5 construction. But what it states is the exterior walls need to be of non-combustible construction. However, fire retardant treated wood is allowed to be used at the exterior wall. So, any other?
Yeah. Let's see. Questions on shear wall design. Is there one method that is more efficient than others for perforated or segmented or FTAO? I can provide some comments, and Michelle, feel free to jump in on that one. So in general, if you're using a fully sheathed wall, perforated would be more efficient than segmented, because you're able to take advantage of a sheathing that is already there. When you're comparing perforated walls to force transfer around opening walls, or even comparing segmented to FTAO walls, that becomes one of those matters where the geometry of the wall can have a big impact. So if you are in a situation where you have many, kind of tall, skinny, high aspect ratio piers, Michelle, I think, alluded to the fact that FTAO can be a little more forgiving when you're using the shorter pier heights on those walls. So there's not one method that, the methods are functional, they work, if for your building. I wouldn't say there's one method that is better or worse than others. I think it is just dependent upon your structural geometry, and the size and the location of your openings can have a very big impact on that.
Right, and one of the, you see some efficiencies in your anchorage. For example, for this segmented, just looking at this wall in the middle, you would have possibly a hold down at each full height wall if this was a segmented shear wall. Whereas for overturning of a force transfer around openings, you have a hold down at each end of the force transfer around opening shear wall. So let me see, like here, you'd have an anchor here and here. And then for the perforated shear wall, your required capacities of that hold down for perforated is going to be higher. There's a higher demand because they want to make sure that this is anchored correctly and that the failure goes up into the shear wall rather than at the anchorage at the bottom. Okay, any other questions that we want to cover here?
It looks like they've slowed down. Yeah, we had a lot of really good questions today.
Do you want to, someone had mentioned about the timber rivet connection.
Oh yeah, yeah. So timber rivets, what was the question on those? I thought I saw it.
Why does it provide higher capacity? So many fasteners.
Right. So yeah, there were some questions that dealt with the spacing of the rivets, and we had talked about, you all were paying attention. We had some people asking about splitting, and that's a very astute question. The holes on the rivet plates are going to be spaced to allow the fasteners to minimize splitting. So we have, if you go into chapter 12 in the NDS, there are specified distances for end and edge distances, as well as spacing of fasteners within rows and between rows. And that's in chapter 12 of the NDS. So the holes in the plate would be positioned in a way that would be a concern that would be minimized. Also, remember when we talked about the scale of the fastener compared to the scale of what it's being attached to? In this case, we're using these timber rivets typically on very large glue lams, and the rivets themselves are not that large, from a relative standpoint. So the risk of splitting would be minimized because we are putting a small fastener into a very big member.
Right, and think of it as if you were looking at those straws, and what if you had a needle into those straws and a bunch of different needles in that straw? That's not going to really decrease the integrity of that wood member. Whereas if you had a big, huge bolt in that member, you're going to interrupt those fibers or the grain of the wood also. Can you tell me a little bit about these connections and what's unique about that?
Yeah, they actually are pretty unique. They're the ultimate square peg round hole. Well, I guess they're kind of oval peg, but so what happens is as you hammer the timber rivet into the main member, your wood member, it's going to deform the steel plate around it, and what that does is it actually creates a lock almost. It gives you a bit of headlock at the top that will deform the plate around the rivet, so you get a very, very tight connection there.
Yeah,
and as again, yeah, and as we said, that these are pretty large rivets. So when you start combining multiple rows of them, you can have very large capacities on these connections.
And what's interesting is, well, one thing, in the NDS, there are specific patterns for these rivets, but when they drive these rivets into the member, they actually drive them in on the perimeter of the connection. So if this is a connection, they're driven in here, and it kind of compresses everything, and they go in and in and in, circular in, so they're compressing that wood in there when they're driven in a little bit.